Okay, so now we've learned how light behaves. We learned that it travels as a particle and a wave, that all wavelengths travel at the same speed in a vacuum. Now we need to look at how we use them in astronomy, how it teaches us about what's in space. So this is a picture of a histogram. And a histogram is simply a light wave that we're taking a measurement of, and our instruments or our cameras will do the work for us. So this is how much light there is on this side, and this is the wavelength of light here. So these are the visible colors. There are also wavelengths here and wavelengths here that we're not going to talk about today, but the visible colors. And we've measured a star, for instance, and when we do it, our light curve on our instrument shows like this. The very peak here, since this is quantity from this side of the graph, is the very most light we have is in the bluish color. So this will tell us a couple things. It will tell us the color of the star. So that star is going to have a bluish whitish look. But it also tells us the temperature, because temperature is determined by the color, or color by the temperature, either way. So, for instance, we have a light curve here that's peaking in the blue, and that star is called Spica. And when you look at that star, it's visibly blue to us. We can see that with our visible light. If we had a star like this that's yellowish and it actually looks yellow in the sky, then we would know that it would peak. Its highest peak here would not be in the blue range, it would be over here in the yellow range. So these are just examples. So here we have the blue Spica. Now look at the temperature, 23,000 degrees, very, very hot. So that would be peaking in the blue. One that peaks in the yellow, like our sun, is only 5,800 degrees Kelvin. Antares, that's more of a reddish star, 3,400 degrees. So temperature can be determined by the color. And here are examples of that. Here are different colored stars and their respective temperatures below them. So we started getting a thing called a spectrograph. It was a new instrument that worked very much like a prism, where it could split the colors of light. And they would use it on the sun, and when they did it, they'd take this white sunlight that looks white to us, run it through a spectrograph, get the colors of the rainbow, but when they looked at the colors of the rainbow, there were dark lines in it. And they're like, what the heck? What could that be? Why do we have dark lines in the colors of the rainbow? And they stewed about it for a long time. They thought, well, maybe that's the division between wavelengths. Maybe that's this or that. And they came up with different ideas. And it took them a while to figure it out. Well, for us to understand what's going on, we have to review just a little bit about what's inside of an atom. So the first one there in the picture is a hydrogen atom. So we have a proton in the center, we have an electron that orbits it, hydrogen being the most simple element that we have. One proton, one electron. Okay, so on the right side we have helium, where we have 2 protons and 2 electrons, and then the red are neutral neutrons that have no charge. So we have shells. This electron is traveling more or less in an orbit. It wouldn't be flat like this, it'd be more three-dimensional going around. But it travels there, and if it gets some extra energy, it is going to change its location of where it is orbiting the center of this atom. So there's a lot of space in atoms. Let's look at this experiment. So this experiment was done where they took a piece of foil, and the foil was made out of gold. It was extremely, extremely thin, hammered very, very thin. And they took particles that would come out of a machine and they hammered against that piece of foil, and they wanted to see what would happen. So when the particles would come out in this beam and they'd hit this piece of foil, some of them would go right through. They'd pass right through the foil. Some of them would hit the foil at a certain angle and be deflected just a little bit to come off at an angle. Some of them would hit the foil and bounce back. Not so many, but some of them. And they realized that an atom has a lot of empty space in it. So some of the particles got shot through this atom would go right through in the empty space. Others, if they hit the nucleus just right, they'd be deflected and go backwards. And if they hit it dead on, it would shoot them back towards the person that was doing the experiment. I'm sorry, I am messing around with this. Okay, so we learned there's a lot of space. We also learned that these electrons can bounce up and down in these shells. So, why do we have lines in a spectra? What's going on? Well, if we have a spectra that looks like a solid rainbow, that's a solid bunch of light that's coming through a prism without anything in front of it or behind it to absorb the light. But if we start getting lines, we can actually identify what might be in the atmosphere of a star, the atmosphere in a planet, by where those lines are. Because every element on the periodic table has its own fingerprint. So if we look at that first one down, that spectra of sodium, look where its lines are. It has these bluish ones, then some yellow, some thicker yellow, a little reddish-orange one. If we saw that pattern with those exact wavelengths, we'd say, oh, the atmosphere of that sun or that planet has sodium in it. And below that, if we saw the lines that are in those exact spots for hydrogen, we'd go, ah, there's hydrogen too. Or calcium, or mercury, or any number of other elements, because everyone has their own fingerprint, their own identifying marks. So we have an atom. Here's a simple one again. You can see that there are different shells here. So if the electron is up here and it is it's absorbing, if it absorbs a photon, it would have more energy to it because it absorbed the energy of the photon, and this electron would actually move up to a higher shell that we can't see in the drawing. But electrons are lazy, and the lowest energy state are the closest shells down. So an electron would want to move back down. It wouldn't want to be clear up there. And so as soon as it could, it would shoot off the same exact energy of a photon that it absorbed and move down to a lower level. So here's a better diagram of that. Here we have an electron. It is traveling around this atom, around the proton. In comes a photon. It has to be the exact right energy that that electron requires to move up. And every element on the periodic table has shells in different places with different amounts of energy. So this, let's just say this photon had the exact right amount of energy this electron needed. The electron would soak it up, it would get that energy, and it would get the power, and it would jump up to a higher energy level because now it's way more energetic. Over here we have an electron that's traveling around this shell. Okay, so that one gets another photon. Now look, notice it's a different wavelength because it only requires a certain wavelength to move from here to here. It soaked up that energy, it's got the power, it moves up a shell, and now it's a higher energy electron and it travels around, but it doesn't want to stay there. Electrons are lazy. They want to go back to their lower state so that it can spit out that same photon and go back down to the lower energy state. This electron over here can spit out its electron, go all the way back down to where it started, and spit that photon back out. So, this is the clue of what's going on with these spectral lines, why we have lines on our spectra. Okay, so if we have a continuous light behind something, here's the light of a star, and there's an atmosphere or a cloud of something, and it's cooler, it's going to absorb the photons that are coming off of this light. Absorbing, sucking up, swallowing, however you want to think of it, it soaks up that photon energy. Now remember, each one has its own energy. Each wavelength has its own energy. So if it soaks it up, then it is missing from the spectra where that photon got absorbed. So this is an absorption spectra. Now down in the lower right, where we just see a black background and we see lines, that is where the electron got tired, got lazy, spit the photon out, and went back to its lower energy state. Now notice that these lines are exactly the same spot as these lines because they all had the same exact energy. That one lines up over here, this one lines up over here. They are in the same spot because the photons had the same energy going into the electron as it got when it got spit out from the electron. Now we can look at the lines. If there's a rainbow behind it and black lines, it got absorbed. If it's a black background, it's spitting it back out, and that's emitting it. But usually with our instruments, we don't see it this way. We usually see it this way, where our emission lines are kind of a graph form, but they would be in the same exact spots as the ones above it. Same lines, straight up, straight up. That's how we usually see it. So with a star spectra, it contains special lines depending on what's around or that star is made out of. This is very helpful to us. Since we can't go to the star, we can't scoop up a piece of it, take it to the laboratory and analyze it. We look at its light, we look at this where the lines are, and we get spectra, and we can tell what's in that particular star. So each element on the periodic table has all of their own fingerprints, and we can identify things in that way. And there are a few of the credits for these slides. I hope you understood this. If you do not, please be sure to read. I'll post the reading assignment that will help clarify it from the free textbook, OpenStax Astronomy textbook that you can download. Absolutely free. Keep it on your computer, and it's a wonderful, wonderful textbook. Well, I wish I could see all your happy little faces, but this is the best I can do for you for now. Signing off. Bye.